First, I did not grade the midterms yet, so don't hold your breath, but they will be graded. Okay. Today I want to talk about shared memory, but first I want to give a little bit of thought to the Ukrainians who are still fighting. They're pretty tenacious, and for their freedom and our freedom. Okay. But before talking about shared memory, I want to make a little bit of context. So far, we have been talking about small systems. First of all, I gave you all the concepts. We talked about reliable broadcast, causality, consensus, all important things, important basic concepts that you have to know. Today we're going to talk about the last one of that, which is shared memory. And starting next week, we're going to start the second half of the course, which is about bigger systems. So it will be a little bit less formal, but because we will cover more ground, but we will talk about large distributed systems. And the first part of that will be 2 lectures on a method called delta QSD. This was developed by a company in England called P&Sol, and this has saved a lot of big companies. Okay, I will not mention them unless we turn off the video, but there are some big companies in UK and elsewhere that would be very unhappy if they would not have used this approach, because they were doing lots of things wrong, and this approach was used for debugging very large systems. And the basic idea is, how do you predict what happens under high load? So now we're really going to talk about large real-world systems, and so the rest of the course will be about will be a little more practical, but also somewhat algorithmic, and also a little bit more realistic. We're going to talk about what you do when your system has huge load and it collapses and you want to fix it. Well, you need to understand very well how the system behaves. And this is a typical large system problem. Okay, so we're going to start. I'm going to give you 2 lectures on that. And we actually have a very nice event on November 24. There will be a departmental seminar. And the chief scientist of this company will be visiting here. This is a guy named Dr. Neil Davies. And he will be giving a seminar. And so I am kind of considering this as required attendance, but this will be complementing the 2 first lectures I gave. So he will give you some really good insight on his experience with fixing real problems in real systems. So that will be starting next week. Okay? But today I want to talk about the last small system concept. Still very important, huh? Small systems could be distributed databases. They could be Amazon servers or something. So they're still very important. And we talked about some of the concepts, causality, all or nothing, a reliable broadcast, consensus. They have to agree. If database, if you do a transaction and it's distributed, clearly they have to agree that they're doing the same transaction, okay? But it's not enough. The databases also store data, of course. And that we didn't talk about yet. But today we're going to talk about how data can be stored in a distributed system. Replicated data. Okay? And we want to assume, we want to make kind of an illusion that you have one big memory, okay? One big memory where you have memory words that you can read and write. And with this, we know very well how to write programs with this. But the distributed system is not like this. It's message passing. So what we're going to do is we're going to build a shared memory on top of a distributed system. We're going to simulate shared memory using message passing. And this is what all distributed databases are doing. Okay? That's the topic for today. We want to simulate that the distributed system has shared memory. And we're going to make slight simplification to make it easy to explain. Each memory location, I'm going to call it register. And you can read and write registers, like you read and write memory location. So this is very intuitive. It's like variables or objects. And in a distributed database, when I say register, you can think object or you can think relation. A database has tables that are replicated. You can think table. So whenever I say register, you can think of any kind of piece of data, even very large, that is distributed. And the algorithms I'm going to give you today work for all of these things. And if you use a large distributed system, database, for example, Cassandra, which is a very popular one, that system will be using some kind of variation on the algorithms that I'm presenting today. Okay, so this is really important for distributed databases. Okay, basically read and write registers. But of course, it can be more complicated. They can be FIFO queues or whatever, other things. But in this lecture, they will be registers, okay? You may have heard of key value stores. Key value store looks kind of like a hash table. You have a key, and under that key you can store a value or update it or read it, and it's distributed. But the abstraction is a key value store, that it looks kind of like a hash table, or even a memory. The key is like the address, but it can be symbolic address. So that's another example. Something called NoSQL, maybe you heard it about this. So many databases are using these ideas, and we're going to have kind of simplified model, but you'll see it fits very easily with all the databases, okay? Many large applications, so Amazon, for example, uses it all the time. Whenever you do something on Amazon, there's lots and lots of database stuff going on behind the scenes. So they're using very big NoSQL kind of database. Okay, so this is all very, very useful. So another way to call it is consistent replication. If you take a piece of data, you want to make several copies of it on different nodes, and then when you write, all of the copies have to be updated. But when you read, it has to be consistent. Maybe there's some timing or whatever, but still it has to be consistent. This is called consistent replication. So even though you have many copies, it looks like it's a single memory cell. We can also call it single system illusion. Okay. Okay. So replication, of course, is very important, and there's two main reasons for it. So we know that already. Fault tolerance. If one node crashes, the other one keeps going. But also scalability. If I have 20 servers, then maybe I can treat 20 times more queries, okay? Because I have 20 times the power. So fault tolerance and scalability are the main reasons. But it's very important. Fault tolerance is maybe the most important reason, okay? Because you really want your system to keep running. And as usual, failures and concurrency is what's killing you on this, It's where all the algorithms you give, they're going to be fault tolerant and they be concurrent. So anybody can be reading and writing anytime and it will have to work. Okay. Okay, so that's the thing we're going to talk about today. The concept, the basic notion is a register, and all the algorithms I show you, they're going to work on registers. And the registers will have two operations, read and write. This is the basic concept. All the algorithms work on this, but you see that it fits many, many things, okay? And because we have a distributed system, when you do a read, you don't get the result instantly. It takes some time, okay? And the same with the write. When you do a read of register R, you start the read here. This is called invocation. It takes some time, and after some time you get the result. Because maybe lots of stuff going on here, messages passing. It's not like reading a memory on a single core where it takes a couple nanoseconds. Here it might take much longer, okay? So we separate the invocation and the response. And the same for the write. When you do a write, the write takes some time to be done, and when it's done, it gives you a response back saying it's done. Okay? So both the read and the write are like intervals. They have a start and a stop. Okay? And this is register R, but sometimes we'll just use one register, so we won't even give the name of the register. Okay? We just do read and write. But of course you can do for many registers. That's the basic data structure that we're going to implement, okay? And assumptions, well, for simplicity, we'll assume that every node is sequential. So it's going to be reading and writing one after the other, not concurrently. So that means it'll do an invocation and it'll wait for the response before doing another invocation. So this is a read and a write, another read, write, and so on. But of course, this does not affect the generality because we have many nodes. But it's just to make it simple that the nodes are sequential. Also, the register values will be very simple. We'll assume they're just positive integers, maybe 0, okay? But of course, they can be anything, these values. Okay, so I'm going to give you a few definitions. And then we'll start seeing how you can actually implement it. Okay, now we're in a distributed system, so things can fail. And we define an operation as complete if it's completely done. If you do both the invocation and the response. You read the register and it's done. But because we have two things, maybe only one of them is working and the other one doesn't come. And the operation is failed if you do the invocation, but there's no response. Because of course you can have crashes, failures. Okay, so that's one thing. The operation can fail. Another thing is we're going to define some kind of an ordering, because of course if you write a register and you read it afterwards, you expect to read the value that you have just written, okay? But not if they're in the other order. That means it's important to define an order. If I have two operations, I define the proceed order. This operation has two things. Invocation response, here also, invocation response. So the response of op1 has to be before the invocation of op2. You have two intervals. The response of op1 has to be before the invocation of op2. And if that's the case, then op1 is proceeding op2. So they're not overlapping. But they might overlap, of course. If that's the case, then they're called concurrent. And that can happen because these intervals take time. Maybe two nodes, one of them is doing a write, but it's not done yet, and the other node does a read. Now what happens? Do you read the old value before the write or the new value after the write? Okay? So that's important. That's something we have to figure out. Okay? So that's why it's important that sometimes They're concurrent. Of course, this is not going to be really true on a single processor. Huh? The read and the write is taking like 1 or 2 cycles if it's in the cache. So it's like a nanosecond or less. So usually they're not going to overlap. Huh? And we assume they don't. But here they can overlap. Okay? See that? Now we're going to have 2 kinds of algorithms. You see, the algorithms are not so simple. We're going to have 2 kinds of algorithms. They're called 1N algorithms and NN algorithms. And in a 1N algorithm, there's only 1 node that's allowed to write. So everybody's allowed to read, but only 1 node is allowed to write. That's a 1N algorithm. And the more complicated one is where anybody is allowed to write and anybody is allowed to read. Multiple writers, multiple readers. So that's more complicated. Okay? So there's 2 kinds of algorithms. So we'll start with the 1N and then the NN. There's also different kinds of registers. Okay? There's the registers that are like single core registers, where you have a global order, and when you do a read, it will read that you've just written, because there's never any overlap. That's actually a very strong register. We're going to call that a linear register. So we're going to start with something simpler, which is called a regular register. So this is kind of very weak kind of register. It's by far not as strong as reading and writing on a single processor, but there's another advantage. It's easy to implement on a distributed system. Okay? And we're going to define the properties of it. It's slightly more intuitive, but still the formal properties. Each read and write operation completes, of course. But then we have the validity. So what is it doing? The read will return the last value written. That's logical, huh? If I write and then I read, the read returns the last value written. But not always. What if the read and write are overlapping? Okay, then it might be different. So the read returns the last value written only if it's not concurrent with another write or with a failed operation. Huh? That means if the read and write are really separated and they're both not failed, then we have the read gets the value of the write. Otherwise, if there is an overlap, the read has 2 possibilities. It either returns the last value written or some other concurrent value being written, okay? It can't just invent a value. Okay, so that's kind of weird, so I'll show you an example of this. So here we have typical kind of registers, 3 nodes. They're implementing 1 register. This node, so this is when it starts and stops, huh? So this node does a write, 5 in the register. This node reads 0. This node reads 5. Later on, it reads 0 again. And then later on, it reads 5. And this one reads 5 also a little bit later on. Notice there can be overlappings. Huh? Sometimes they don't overlap, unlike this one and this one. But sometimes they do overlap, like this one and this one and this one and that one. So this is kind of weird, huh? Because you never see this on a single processor, huh? If I read 5 and then I read again afterwards, I'm not going to read an older value, huh? Well, 0 is an older value, huh? But here, who knows? Maybe I can, okay? So is this execution a correct execution of a regular register? So let me refresh first. The read will return the last value written, but not all the time. Basically, only if there's no overlap. Okay? Only if there's no overlap. So here, you see what all these reads are returning, huh? 0, 5, 0, 5, 5. Some of them are overlapping, but some of them are not. So there's 1 write here, huh? So is that correct? Regular register? What do you think? according to the way I defined it. Is this one regular? So you have to look at the overlaps. So notice when there's an overlap, things are kind of fuzzy. Yeah? So is that what's happening here? What do you think? For example, I'm writing 5 here, but this read is overlapping with that 5. Is it allowed to return 0? Yeah. Yes, it is. Because when you overlap, then the constraint says nothing. It's only when they're completely separate that it looks nice. When they're overlapping, it's kind of weird. Okay? So here again, here I'm reading 5. Is that okay? Overlaps. It's okay? What do you think? Yeah? But here afterwards I'm reading 0 again. Notice there's also overlap here. Is that okay?
Yes.
Yes, huh? As long as we're overlapping, it can either be the old value or the new value, basically. This one is reading 5. Is that okay? Notice it's not overlapping anymore.
Yes.
Is that okay? Yes, huh? Could this one read 0? If this one were to read 0, would that be okay? No, because it's not overlapping anymore. Then you have a condition. Notice the regular register only really imposes something when the operations don't overlap. Okay? This one also does not overlap with that. So this is a correct regular register. This is kind of, compared to variables that you know in programs running on a single core, it's not the same. It's a lot weaker. You have this funny behavior when there's overlap. Why do you have that? Because we're in a distributed system, and if you allow that, it actually makes it a lot easier to implement, okay? If you don't want to allow that, if you want a true single storage illusion, it's harder. That's why we have regular registers. Sometimes this is good enough. This is kind of weak form of register, Sometimes it's good enough, okay? Okay, now let's make an algorithm to implement this. Okay, so here's an algorithm. Very simple. We designate one process to be like the leader. If you want to read, then you send a message to the reader, you ask him for the value, and he sends the value back. If you write, you send a message to the reader saying, here's the new value to the leader, and the leader sends an acknowledgement back. That's reasonable, Of course, maybe it's not so nice, as a distributed algorithm, I mean, this algorithm has some obvious problem, What's the problem? I mean, it works. Every node will see a register, right? But of course it has a problem, What's the problem? This algorithm. Obvious problem in a distributed system. Right? What do you think? Yeah?
A second node might write a new value before a previous read message.
But actually, it's actually correct. If you do read and writes that are not overlapping, then you're fine. If I wait for the acknowledgement for the write before I do the read, that means the leader will see purely sequential requests, and we're good. So it's a correct regular register. But still, I mean, it's correct, but it's kind of a weak algorithm. There's like a major weakness here. Yeah?
If the leader crashes.
If the leader crashes, exactly. It's it's not very fault tolerant, Leader crashes, you're dead. So we don't really like this because it's not fault tolerant. That's why we're going to move towards the n algorithms, So the 1n algorithms will have this weakness of the writer, but the readers will be n. Okay, so let's try to make a smarter algorithm. Well, I call this first one bogus because it'll have a bug. But the intuition is very easy. This is a slightly different algorithm. So I have n nodes. It's very easy. The writer will write to all the nodes, and the reader will read the local value. That's reasonable. That's intuitive, huh? So if I have 10 nodes, if I write 5, I will kind of broadcast 5 to all the nodes. And then when I can read any node by just reading the local value. That's kind of intuitive and reasonable, huh? Right? So here, for example, here's an algorithm. When I do a write, well, I update the local value, I broadcast. So I'm doing a for all, huh? A for all, and I send V to every node, and when it receives the message, it updates its local value, okay, and that's it. And the read will just return the local value. So this is another algorithm. But this algorithm is actually buggy. That's why I call it bogus. So this algorithm has a clear problem, huh? You have to understand, the broadcast, you're just sending here, huh? You're not waiting for acknowledgement, huh? You only send, huh? Send to all the other nodes, and then you immediately return. So what happens when you read? Maybe, right? I'm not saying it yet, but... So this algorithm is kind of problematic. I mean, the core idea is nice, but it's not really the right implementation yet, huh? So for example, so this one is a problem. If I do a write on P2, it will send 5 to P1, but that might be very slow. So this guy has not arrived at this message. I do read 0 again, and then it arrives, and then I do read 5. Well, that's not good because this one is not overlapping with that one, so it should read 5. Huh? So this is buggy, huh? Right? So how do we fix it? Well, we need a little bit more synchronization here. So now I wanted to show you our first algorithm. This is called ReadOne, write all 1n. Okay, this one is going to use a perfect failure detector and fail stop. That means you can just crash, but you will detect the crashes. Okay, that's reasonable, huh? So here's part of the code. I will update the local value. I broadcast to everybody. But there's something missing, huh? And then I return, and the reader will return the local value. So here I have to add acknowledgements, huh? Because when I read, when the write is done, when it's completely done, the read has to return the new value. That means the write has to take a little bit longer, huh? It has to get acknowledgements, huh? So it has to do something like this, huh? Wait for acknowledgement from all correct nodes. And once it gets that, it's done. And then, if I do a read, it'll be good. Because if there's no overlap, then I'm sure this local value will be right. But if there is an overlap, then it might be wrong, huh? It might still be the old value, but that's okay for regular registers. See, it's getting a little bit trickier, huh? You see, as we try to make the algorithm better, things get a little bit more complicated, huh? Okay. So the idea is like this. This is our first algorithm, which was wrong. You do a send, which is very slow, and you do reads, and eventually the reads will see the new value, but these two guys are incorrect. But the new algorithm is like this. You do a send, and you wait for acknowledgement. So the write in the second algorithm is actually a very long interval before it's done. That means these two will still see 0, but now it's okay because they're overlapping. We make the write long enough so that it covers these two. And this third one will be not overlapping, but it will see the new value, because it's after the acknowledgement arrives. So the idea is to postpone the writes. You make the write slower so that the overlaps are inside the write, in a sense. So kind of the weird overlaps for slow messages would be inside this long interval. So basically, you make the algorithm correct by making the write slower. Okay, you see the idea? So that works, but it has, of course, some problems. It needs a perfect failure detector. And you know, one of the themes of the course is you start perfect, but you end up imperfect. So perfect is like the ideal world, but real life is not perfect. So you have eventually perfect. So that's what we're going to do now. What if you don't have a perfect failure detector? What can you do? We're going to use a similar trick as we did before. We're going to use the majority idea again. Okay, so I'll give you now another algorithm which does not need failure detector. So it's called FailedSilent. FailedSilent means you crash, but you don't detect them. You have no failure detector, so it fails silently. You don't see it. Okay, FailedSilent. So it still crashes, but you don't detect it. Okay, so the idea is to use a majority idea. Whenever you write to a majority. Whenever you read from a majority, which might be different majority. And what can you tell me when I have two majorities? What is the trick when you have two majorities? You have to know. When you have two majorities, what can we say? When you intersect them, for example, what is it? It's always
the intersection not empty.
The intersection not empty, That's the trick. Okay? That's a really important, let's call it technique, okay? Not trick. I won't call it hack, okay? You didn't hear me say that. It's a technique, a very smart technique. So here's an example. So here we have a bunch of nodes. So there's 9 nodes here, okay? So the majority is 5, So I write. How do I know that I've written to 5 nodes? Well, as usual, I write to everybody and I'm collecting acknowledgements. As soon as I have 5 acknowledgements, I'm good. Maybe the other 4 nodes have crashed, who knows? But as soon as I have 5 acknowledgements, I'm good. I've written to a majority. And the read is the same. I will ask for values from all the nodes. And then I collect values coming back. As soon as I have collected 5 values coming back, I'm good. Okay? And then there's at least one node, in those 5 values, there's at least one node that has seen this value of the write. So the trick then is, how does the read know which one of these 5 nodes has the right value? And that's simple. We're going to have some kind of sequence numbering. The writes will be kind of numbered, and the one with the highest number is the one we take. Okay, so this is an algorithm that does not require a failure detector, and it will work up to just less than half of the nodes failing. Okay, see that? So there's the intersection. And it's actually a general principle. It doesn't have to be just majorities. Majority is symmetric. I have 2 majorities. But we can do trade-offs here. We can make the write set bigger and the read set smaller, for example. We can say, we read from R nodes a number R, we write to a number W. As long as R plus W is bigger than the total, we're good, huh? So here we have 9 nodes, we write to 5, we read from 5. 5 plus 5 is 10, it's bigger than 9. But we could write to 8 and read from 2. It would still work, because they would still intersect. Sometimes that's better. Maybe the writes are very fast and the reads are very slow, so we don't care if we do a lot of writes. So that would be another way, huh? And so I'm going to give you an example of another kind of quorum. So the majority is what we saw. And it has 2 points. A pro, a good, an advantage, and a con, which is a disadvantage. The pro is a con, it tolerates up to just less than the majority of crashes. So the ceiling of n over 2 minus 1, so just below half. But the bad part is you actually have to read and write half of the values. So here it tolerates 4 crashes, but you actually have to read or write 5. That's kind of a lot. So we can trade off here. So here's another one. This is actually maybe a one that's kind of very smart in some ways. This is called Maikawa quorum, because a very smart guy named Maikawa came up with this idea. Here's another way of organizing the nodes. Here we have 9 nodes, again, like here, but we arrange them like in a square. It's just kind of a logical arrangement. Of course, they don't change in the network. So they're like in a square. Whenever you write, you make sure you write to at least 1 row. And whenever you read, you make sure you read at least 1 column. And a row and a column always intersect. Isn't that clever? So the idea is you will write nodes and get acknowledgements until you have gotten acknowledgements that at least 1 column is, 1 row is written. And the same for the reads. You will get values. Basically, you ask all the nodes for values, because some of them might crash. You get values until you have 1 column. And that means the row and the column, you have 1 row and 1 column, and so you have an intersection. So this has a different pro and con. So there's much advantage here. You only need to read and write square root of n nodes. So you can start by just writing this column for this row, for example, and if it doesn't work, you start doing others later, only if there's failure. So minimally, you only have to read and write square root. That's a lot less than n over 2. But there's a disadvantage. You will only tolerate square root of n minus 1 crashes. Here you will only tolerate 2 crashes. So if 2 nodes crash, that will, if you crash 2 nodes here, for example, then maybe there's only 1 row and column that will work, which is this one. If I crash these 2, that means it still works. But if I crash 3 nodes, maybe there's no more row and column that works. Okay? So in order to guarantee that it works, you can only crash square root minus 1. But maybe that's okay. In real systems, the number of crashes is usually small. So maybe that's fine. You're not very fault tolerant, but you only have to read and write many less nodes, square roots. It's a lot smaller than n over 2. So you see, with the quorum idea, you can kind of adjust what you're doing. Okay, so here's how the algorithm works. We assume, we're going to show it for majority, but it works for any quorum. You assume majority of the processes are correct. That's the assumption. And you will have a sequence number. And it's a 1n algorithm. So only one of the nodes is going to be doing a write. Okay? No failure detector. So here's the write. you broadcast the value and the sequence number to all the nodes, and you wait until you get acknowledgement from majority. When the receiver receives feed, it updates the local value. And once you do that, the write is done, and you increment the sequence number. This is increment, so that the next time you do write, you'll have a higher sequence number. Okay? See how it works? And the read is the other side. You ask, you do a read request, you send a message to all the nodes saying, what is the value? Each one of them answers. It gives you the local value and sequence number, or maybe nothing if it failed, of course. But all the correct nodes will answer, giving local value and sequence number. And you basically wait until you get values from a majority. And once you have that, you pick the value with the highest sequence number, and you're done. The highest sequence number will always be the most recent write. Okay? So that's nice, huh? That's pretty good, huh? So this one does not need a failure detector. So we've made an improvement, huh? Of course, there's a small detail. It's almost correct, huh? This algorithm. There's a small detail. It's related to the orphan messages from the previous. So here's an example. This one, P1, P2, P3. P1 does a write of 2, and there's 3 nodes, so the majority is 2. So it stops here. And then P1 does a write of 5. Okay, ping, ping. And majority is 2, again, so it stops here. But notice, then there's this very slow write message that comes here. And now we do a read. And somehow this read picks up this from this slow message. And also here, the local, it was a majority, but it never updated this P1. So the majority will be 2. So that's not good, huh? 2, you write 2, you write 5, and then you read 2. So what's the problem here, actually? It's this one, huh? So how do we fix that? That's easy to fix, huh? You see how we can fix that? You recognize that it's kind of similar to the orphan message problem, huh? Where you have rounds, and a really slow message from an old round survives and managed to come into the current round. But that's actually easy to detect. Huh? Here also, how can you detect this? How do you detect that? You can actually ignore this one. Huh? How can you ignore this one? Very easy, no? Isn't it? You have sequence numbers, huh? 1, 2. So P2 has already gotten a message with sequence number 2. But here it gets a message from sequence number 1. Yeah?
We can discard the previous messages.
We can discard the messages with the old sequence number. Yeah, that's right. So we can discard this one, huh? Because it's an old sequence number that comes back. Okay? So basically the way to fix it is the receiver will only accept this if it's a newer sequence number. Okay? This is we have to get rid of the orphans, huh? But then it works. Then we're fine. So this is not bad, huh? This one gives us regular registers, and it will support lots of crashes, does not need failure detector. So it works on the internet. But it still has some limitations, huh? It's only a 1N algorithm. Only one node is allowed to write. Maybe we want more than the write. And it's only regular registers. Maybe we want really true single store illusion registers. Okay? Okay, so that's the next step. So up to now, we have shown just regular registers. So they're kind of very weak, because when they're overlapping, then you basically don't know what's going to happen. That's kind of not nice. You really want registers to write at an instant, and anybody who reads after that will read the new value. So you want like really single storage. So let's try to do that now. We can do that too, actually. Let's try to go to a true single storage. So regular registers, I showed them because they're easy to implement, but they're weak. Sometimes they're okay, but sometimes you need single storage. Okay? And single storage, now we have to define it. We have to make a rigorous definition. And there's actually, the definition is actually a safety property. Okay? That means some executions are allowed, but others are not allowed. So it kind of prunes the way. Certain executions are not allowed. It's a safety property. We can make a mistake. If we read an old value, that's a mistake, and we've broken the system, huh? So that's typically safety, huh? And so there's actually two ways of defining these single storage. There's what's called sequential consistency, and the other one is called linearizability or atomicity. These are synonyms, huh? I'm giving you the terminology that people use, kind of weird. Sequential consistency means it looks like you have a single core, but only per node. That means on each node, if you do a write and you read, you will see the value. But in between nodes, they can be shifted. It's not global. It's only per node that it's single storage. Huh? You do write and you do read, after, it will see the value written. Okay? But if you do a write and you do a read after on another node, it might not. So sequential consistency, we say it's only local time per node. So it's like each node is obeying consistently, but not in between the nodes. And then the strongest one, the real one, the strong one, the true global single storage is called linearizability. Single system image and global time is obeyed. That's very strong, huh? If I do a write on this node, any read that's done after, anywhere, on the whole system will see the value written. That's pretty neat, huh? How can we do that? How can we trick the system? We can't send messages infinitely fast. That's a very strong property, huh? That means if I read and write on all the nodes all over the world, it's as if, whenever I do a write, it's as if the write is instantaneously done everywhere. How can we do that? Isn't that funny? Yeah?
Doesn't the computation theorem prevent us from obeying global time?
Sorry?
Doesn't the computation theorem prevent us from obeying global time?
I'm sorry, the computation theorem. Ah, yeah, it does actually. But it's not actually, it's only, you'll see, we actually, we kind of go around the computation theorem. Because the global time, it's not something you can measure. There is a global time, but it's kind of hidden, but you'll see. So we're not actually contradicting the computation theorem here. Because the global time, it's not a time you can measure. That's kind of weird, but I'll show you what's going on. You'll see what we define when we show how it works. Because this seems like it's impossible, huh? As like this. You can't send message instantaneously. So how does it work? Well, it's actually a very clever trick, as usual, for distributed systems, which you will see. Okay. First, some examples. Okay. So here's an example. I do write 5, and I do, on another node, I do read 5, read 0. Now this is a good regular register, huh? Because they're overlapping, and so it doesn't matter. But sequential consistency does not allow that. And why does it not allow that? It disallows this behavior. Why does sequential consistency I mean, as a regular register, this is fine. But as sequential consistent register, it's not good. You see why? Sequential consistency, it's consistent but per node. So you have to look at P2. So what happens on P2? So sequential consistency means as soon as you do something, later on, it has to be consistent with that. So if I read 5 here, if I read again, it has to read 5, okay? Because it's as if the thing was consistent per node. So I can't read a 0 after reading a 5. That's not sequentially consistent. You see that? Per node, it has to be as if it was running globally consistently. That means every value, whenever I read a value, I have to read that value forever afterwards until I do another write. Huh? That means I can't do read 0. You see that? So this is not sequentially consistent. Okay? On the same node, those two have a connection. Huh? So here, now let's talk about linearizability. Linearizability is like sequential, but it's global for all nodes. So it's stronger than sequential. Huh? Sequential is per node, it's consistent, but the nodes might be shifted. But linearizable means the whole system is perfectly consistent with a global time. Of course, this cannot work in a linearizable system, huh? Because this one would have to read 5. But if this one were to be done on P3, then it could still not work on a linearizable, huh? But as sequential, it would work, huh? You see that? Because the sequential allows you to shift the nodes with respect to each other. Okay? So here's one. So here's another one. So is this sequential consistent? Yes. Why is this sequentially consistent? Because clearly I'm reading 0 after reading 5. But that's okay for sequentially consistent. Why is it okay? Because they're on different nodes. Because the nodes are allowed to have a shifted time. But if I were to do another read on P3 after this one, then it would have to read 5, huh? But if it's on P2, no. But now we can see a difference, okay, with linearizability. Now this one is not allowed in a linearizable register, huh? Because here we do have a true global single global consistent storage. That means if I read 5 on P3, and if I read later than that on any other node, I have to read at 5, okay? Unless I've done another write, but here there's no other write done. I have to read 5. No single storage could behave like this. See, here all the times are synchronized with each other, huh? That's the difference between linearizable and sequential consistency, where it lets you shift the times. Okay? Okay, so that's how, those are the two kinds of global system. Okay? Now, we can compare sequential, consistent, and regular register. Okay? We cannot say that one is strictly stronger than the other. Okay? We can have a sequentially consistent execution that is not regular, or we can have a regular execution that is not sequentially consistent. Okay? And so here we have a sequentially consistent execution. It's sequentially consistent. Why is this sequentially consistent? Why is this one allowed to read 0? It's allowed to read 0 because we can we're not comparing between nodes. There's no other operation on P2. So there's no inconsistency. If we were to do another read before this, it would have to read 0 as well. Huh? Afterwards, we don't know. It might read 5 at some point. Huh? But this is not allowed for regular registers. Why not? Why is this not allowed for regular registers? Regular register, the trick is the overlaps, huh? Yeah?
Because we're reading 0 even though it's been written 5.
Right, we're reading
and
0.
And it doesn't overlap.
Exactly, even though it doesn't overlap. It's after, it doesn't overlap. In a regular register, this one must read 5. But in sequentially consistent, we don't care about the overlaps. We just care about the consistency along this line. And we're fine. There's only actually one operation here, so there's no problem, okay? Okay, so that's the definition. But we're going to make some algorithms now. But let me make a break first. So we make a break, and after the break, we'll see the algorithms. Okay? Let me now show you a linear consistent algorithm, a linearizable algorithm, linearizable register. Okay, I will do that one because that's really the nice one. Sequentially consistent is sometimes useful, but the real important property is linearizability, the strong one. Okay, but before that, I want to talk about liveness. Notice that these properties are safety, and I can't really keep going without saying something about liveness. Now, liveness is quite different, actually, for these kind of registers. And so I'm going to just give you a little mini summary of liveness properties. Remember, liveness is when the system makes progress. It actually does good things. So it's totally different from safety, of course, huh? And there's 3 interesting liveness properties for this kind of system. The best one, the strongest one, is called weight-free. Weight-free means that every correct node advances. So I have a big system, 100 nodes. Big system, 100 nodes. And all of them advance. No deadlock, no live locks, and no starvation. You know what deadlock is, huh? Right? Remember? You have like a cycle and resource graph, but you also have a concept called live lock, when each node is kind of picking this part of the resource from the other node. This is when you can steal resources. So their nodes are spending all their time stealing the resources and they're not doing any work. And starvation, of course, is like a scheduler thing. But here you have none of that. Every node progresses. That's the strongest one. Then you have a second one, a little weaker. At least one correct node is progressing. That means no deadlock, no live lock, but maybe starvation. All the nodes are being starved except for one. We're only interested in one node. That's weird, huh? But that's sometimes important. And then the weakest one of all is called obstruction-free, also called solo termination. So here we have one node, but if we don't interfere, if it executes without interference, it will make progress. That means there might be line lock. That means other nodes might be stealing this guy's resources all the time, so he doesn't make any progress, so nothing happens. But if they wouldn't steal it, the guy would make progress, okay? So these are the 3, but I like to make it very intuitive, so I've made kind of intuition in terms of sports. So the weight-free is like a marathon where everybody tries to win. Everybody is in it for himself or for herself to win, okay? That's the marathon. But the lock-free is more like Tour de France, when I have a team. And the team, they only care about one guy in the team, okay? And they're all helping this one guy to be the winner, to get the yellow jersey, whatever, huh? So this is where you only, one node per team is actually needs to make progress. We don't, the others could all, they could all crash and burn as long as that one guy wins, okay? So that's kind of like lock-free. And then the final one, this is football game, soccer, football game. If I'm dribbling with the ball and I want to make a goal, someone can steal the ball from me. Then I take the ball again and I'm trying to make the goal. Somebody can again steal the ball. But as long as somebody is not stealing the ball, I can make a goal. But people are allowed to steal. So if I can execute without interference, I can make a goal. But I could have interference. And if there is interference, I might not make a goal. So this kind of shows you the three. So for Tour de France, the liveness requirement for Tour de France is actually lock-free. You can actually, next time you're having a beer for Tour de France, you can say that it's lock-free. And in a football game, you can say it's obstruction-free. This is the technical terms. Okay, so I'm saying something about liveness. So let's get back now to linearizable registers, also called atomic registers. Okay. So before the break, I explained it's kind of very tricky. How do we make it seem like there's a global synchronization? Whenever I do an operation, it happens instantly in the whole system. So when I do a write instantly, and then I do a read a little bit after, 5 nanoseconds after, anywhere, and it will read that written value. How can we get that? Well, the trick is we don't actually get that, but it appears as if we get that. Okay? We have what's called linearization points. Whenever we do a read, it's like an interval. Then it's as if the read was done instantaneously at some time in between the invocation and the resound. We don't know which time, but we know there's some instantaneous time there. Okay? So you see, we're not disobeying the computation theorem because there's no specific time here. There's no specific event. And the same for the write. When you do a write, it's as if it was happening at some point. I mean, we don't know where. It's just that point has to exist. Okay, it has to exist. There has to be some point, and it could be as if it were happening instantaneously at that time. Okay? Of course, we have to worry about failed operations. And those are they either completed or they never occurred. Okay? Okay, now let's investigate that. These linearization points. I'm going to show you some examples, of course, but let me show you first two definitions of linearizable. Here's the one with linearization points. Things are happening as if they were instantaneous, but we don't know exactly when, but we know there is a time. But we can also have a more ordering kind of definition. So here, what I'm doing is I take the definition of regular register and I add something. So this validity is actually same as regular register. It returns the last value if not concurrent or not concurrent with failed. Okay? And if I add an ordering condition, then it actually becomes the same as this. Okay? It's just to have another definition. So if a read precedes another read, then the write of R1 has to have preceded the write of R2. It means reads and writes cannot be switched. Okay? Okay, so that's just something I'm telling you, but let me show you some examples. Okay, here is an execution. It looks kind of weird. I write 5, I write 6. But during this write 6, I read 6, and then I read 5 a little bit later. Now, is this an atomic execution? The question is it as if, can we find instance in time where the reads and writes are happening as if they were happening at that instant everywhere? Okay. Here, maybe not. So there is some conditions here. We can actually make like consistency conditions. Okay. So what would have to be true for that to be true? So here we have a read 5 before the read 6. Okay. Here a write 5 before write 6. We have read 6 before read 5. Okay. So we can actually set up kind of consistency conditions. So in this example, no, this cannot be atomic. Why? Because we can make some conditions. So look carefully. If I do read 5, then the instant that the write is done, the write 5 has to be somewhere here. And it has to be before the instant the read is done. So these are times. The write has to be before the read 5. Okay? Now, the read 5 has to be before the write 6. Okay? Because the write 5 is before write 6. And the write 6 has to be before the read 6, of course. Because you can't read a value until you write it. That means that the write 5 has to be before the write 6. But we know the read 5 has to be before the read 6. But we know read 6 is before read 5, so that's inconsistent. So it's not possible. But let me show you an example where it is possible. So here, for example, for this example, notice we write 5, write 6. Here we read 6, read 6. We can define instance in time. Okay? So, for example, assume the write is done at this instant. Exactly at this instant. Okay? And the second write is done at this instant. Exactly then. In order for this read to read 6, the instant for the read has to be later than that, of course. And in order for this read to 6, it has to be later as well. But that's okay. We can find it. We have found 4 instances. It's as if the write was done instantaneously here, and the read is instant. And if with these points, this is consistent with global consistency. Okay. Okay, here's another one. A little bit more subtle. Here we read 5, read 6. But this read 5 is overlapping with write 6. So we have to be a little bit careful here. Okay? So we write 5. Okay? We read 5. Okay? Now the write 6 has to happen after. Because if it were happening before, this would be reading a 6. So it has to be after. But luckily, we have some space here. We can actually find a place. Okay? Could be there, for example. And the final read, 6, is here. So with these linearization points, this behavior is consistent with global single system image. Okay? See how it works? So we don't actually have to know the times. We just have to know they exist. And the system behaves as if it has a global single system image. Okay? So this is just taking a step back for a minute. This seems to be a common theme in distributed systems, where we play around with knowing something or not knowing something. In a partially synchronous system, you know that it eventually becomes synchronous, but you don't know when. But you know it does sometime. You also know there are bounds, but you don't know what they are. All you know is that they exist. So that's a funny kind of knowledge. Here it's the same kind of knowledge. You know that these points exist, but you don't actually know what the values are. Maybe you could figure out some values, it would take some effort, but you don't really know these values, huh? Okay? So now let's try to make an algorithm for this. We're going to extend the algorithm for regular registers. Remember, regular registers are actually, everything is okay as long as they don't overlap. So there's this overlap business we have to worry about, okay? So the standard regular out system does not work. You have to extend it, okay? The standard regular register algorithm, so the majority vote algorithm does not work. So this one, for example, is regular, but it's not atomic, okay? It's not atomic. We have to do a little bit more to make it atomic, huh? So here's, for example, to show how it works with the regular, huh? So here we have, remember, regular we did majority for the writes and majority for the reads, huh? So we have write majority here. We have read majority there. We have read majority there. And now we have a write majority here. So these majorities here, they're not good enough to make it globally consistent. Okay? So how do we make it globally consistent? Well, we have to add something. We have to do a little bit more. And the thing we do more is, it's called read impose. The problem is, we have these reads. These reads, when they overlap with the writes, they can be wrong, okay? You read 6 and you read 5. How can you avoid it being wrong, okay? Well, one trick or technique is to change how you do a read. When you do a read, when I read 6, the algorithm that reads 6 will internally also do a write 6. And that means the later guy will see the write. Or it will, if it doesn't, there will be a longer interval. So the read, in order to make sure that the reads, later reads will see the right value, the read will do a write. Okay? When reading, it also makes a write. Now here, the write, it means it has to do a write with a majority, collecting, so this interval can be longer, okay? And now we're good. Now we can write 5, read 5, write 6, and read 6. Now we can find linearization points, okay? The idea is we've added a constraint to the read, okay? Yeah?
How does extending the time period of undefined behavior help us?
Well, because it gives you more, you have more liberty in picking the linearization point. It has to be somewhere between the invocation and the response. Now, this is an example. It might be quicker, but if you actually read a 5, assume it's not a 6. This is actually reading 5. But if I write 6, how can I write a 6 and read a 5? The only way that can happen is if the write, somehow the acknowledgement took very long, and so it kind of spreads out to here. That's the only way that can happen. That means the read 5 actually has somehow early, has seen it before that the write has been done. So this is how it looks, but the point is that the only way you can read a 5, if this one will now write 6, how can this one write a 6 and this one can read a 5? The only way is if the write is very slow. It could be. Then the read can work. This is still the regular, I'm still looking at the regular register algorithm. I've just added a write inside here, okay? So the results are still the same. But now I can actually find linearization points. Doing that it actually stretches out. In this case, it stretches out the right, because otherwise, there's no way it could be 6 and 5. See that? So this read is doing a write 6 with acknowledgements. But how can it get acknowledgements of 6 and this one's still reading a 5? It can only work if the acknowledgements are happening very late. Okay, in this example, so this one will read a 5 with acknowledgements, and this one will read a 6, but in fact later, because it has written a 6. Okay? But you can also prove that the reads and the writes are not switched, in fact. So this is my other definition of linearizability. So this is regular register, and I add a condition. If the read precedes the read, then the write has to precede the write. Okay? Now, the write, there's new writes here. So the write has to precede the write. So I'm writing a 6 here. Okay? So that's how you can prove that. So let me maybe I come back to this because it would take more time to explain. But so this, in fact, the idea is that you're making a write while you're doing a read, before you respond. So when you do a read, you're getting the acknowledgements, but you find out what is the value I'm reading, but then before you respond, you do a write with the acknowledgements. Okay? Now there's an optimization you can do here. I'm not going to say much. So it's also with sequence numbers, If the majority have all the same sequence number, then you don't have to do the write, but that's okay. Okay, let me now go to the final algorithm, and there's another technique here. So the previous algorithm, the read did an impose write, okay? But now I want to do multiple writers. So this is the most sophisticated algorithm, okay, that I want to do. This is a linearizable with multiple readers, multiple writers. Okay? And the problem with this is that each of the nodes has its own sequence number. Okay? So each node will be counting a sequence number whenever you do a write. You increment. So the writes per node are increasing. But in between nodes, the sequence numbers might be not synchronized. Okay? For example, here I might have sequence number 28, and here I have already sequence number 30. I've done 30, right? So this one would be ignored, but that's not allowed. That means I have to do something about the sequence numbers on the different nodes. Okay? So, so this would be ignored. So this is the final algorithm, so I add another phase. So the read is still the read imposed. That means the read does also a write. So the read is doing read and write. And the write will also do some extra work to get the sequence number. It's called write consult majority. So before doing a write, I will ask from a majority of nodes to get the value of the highest sequence number. So I'm up to date with the sequence number, okay? And it's a majority. I'm doing always from a majority, to get the sequence number, and then I can do a write with that sequence number, +1. And if I do that, then it works. Okay, so I'm not going to give you proof of that, but it works. Now, it's possible to get two concurrent writes with the same sequence number in this kind of algorithm, and you just need to do a tie break in that case. For example, the two process IDs, you compare them, and the one with the highest is the one that wins, for example. Okay? So that's the final algorithm. read, impose, write, consult majority. And a final little point on that. What if I'm doing a write, but I somehow get an old write in another node then what do? Do I still have to send the acknowledgement for the old one? But actually I do, because that old one has to complete. Okay? So let's say I have two nodes. There's a slow one doing write 5, a fast one doing write 6. Okay? So this one completes, receives the acknowledgement. Okay? But the slow one, it has to complete. So you have to send the acknowledgement, even if it has an older sequence number. Okay? Because the writes have to complete. Okay. Okay, so that's the most complicated algorithm, and I'm not going to show you the pseudocode for that. Okay? But you get the idea how you do it. So it gets complicated. Huh? Okay, now to finish up, let me talk about message passing and shared memory. So there's two ways of making concurrent systems. Huh? Distributed systems where you have independent nodes sending messages, or you have threads looking at a shared memory, and they're basically reading and writing the shared memory. And we have today simulated shared memory. Now the registers are seen by all the nodes, and they're read and written in consistent way. Okay, so we've seen how to simulate shared memory on top of message passing, and the only condition is that we need a majority of correct nodes. So that's one direction, huh? Simulated shared memory on top of message passing. Now you could ask the opposite question. Can you simulate message passing if you have shared memory? So assume I have a system like a multi-core architecture with a shared memory. So this guy has a shared memory, but I want to simulate a distributed system on that, doing message passing. Can you do that? Is that possible? Yeah?
Yes, I would say yes, because, for example, when we used us, we did message passing without having multiple nodes. So
you can implement message passing, but how does it work actually? How do you have these independent nodes that are sending messages, but the underlying system is shared memory, right?
Yes.
So how does it work?
I would for in the case of us, I don't really know, but for example in Erlang, it's like a mailbox.
A mailbox?
On which we send a message to
right.
an agent. The message is stored in the mailbox, so we can just say it is stored in memory. And then when we use it, we just remove the message from the memory and use it to treat it. So maybe we can just have different memory banks where we store messages, process them. And
okay, yeah, so that's completely right. So each thread is implemented in the shared memory system, but then you have the mailboxes, which are basically representing the network, huh? But it's just a data structure in memory, and sending is just adding something to the mailbox, huh? So you can implement that, yeah. So it's of course it's possible, huh? So here it's explained slightly differently. You have a register, and you append to the channel. So the channel is like a mailbox. It's a set of messages or a stream or a list of messages, and when you send, you will add them to that, and then you receive messages, so each thread will take the messages out. Either it can do polling, or you can be smarter, right? So you can have a list of waiting nodes, so each channel or mailbox can have a pointer to the thread or the threads that are waiting for these messages. And then when the scheduler schedules that thread, it actually just takes out the message from the mailbox. Okay. So yeah, so it's very possible to do that. So message passing can be simulated in shared memory. And so you can do both. So in some sense, shared memory and message passing are equivalent. They have the same power. Each one can be implemented using the other one. Of course, the efficiency is not exactly always the same, and the complexity is not the same. It also depends on what hardware support you have. But there's no intrinsic additional power in either of them. Any program that uses shared memory, you can run it on a message passing system and inversely. And actually, systems take advantage of that. So if you have like an airline system, so you reach an airline. In airline, if the two airline processes are running on a shared memory, or if they're actually on different distributed nodes, you don't even see that in the program, even though the implementation is very different. If they're running on the same shared memory, then they're doing like this. But if they're running on different nodes, then they're doing pure message passing as a distributed system. Okay. So let me summarize what we saw today. So we implemented shared memory registers. This is a model of distributed database. We looked first at regular registers, which is the weak kind, and then atomic or linearizable registers, which are the strong ones. For the regular registers, we showed a couple of algorithms. First one that needed a P, perfect failure detector, and then another one that uses majority, but it's still always with one writer. And then the atomic register, we start first a single writer model, and the idea is to make sure that the reads are ordered. You make a read impose. So the read will do a write. So when I do two reads, they will also internally do writes. Okay? And that will impose an order upon them. And finally, the multiple writers, the point is you have to manage the sequence numbers, which are different for each process. And that means that the write has to, before you do write, you have to figure out what is the latest sequence number. So you do what's called a consult majority. You ask the majority, what is the latest sequence number? And this makes sure the sequence number are synchronized. And this is a correct multiple writers algorithm. Okay. So that's how it works. There's some slides on formal definitions. So just very quickly, you can actually make a formal, today I was a little bit informal so that I could present the algorithms, but you can actually look at it formally in terms of events. I remember distributed execution is events. So the invocation is an event, a read invocate event, and the response is a read response event. Then you have a write invocate event and a write response. You can see in the read response, the event has the value. It has the name of the register and the response gives you the value. The write has the name of the register and the value, and the response is just an event with nothing, just telling you that it's done. And so a read operation has two events, okay, an invocation and a response. A write operation has two events. And then we can now define what it means to have sequential consistency and linearizability. Okay, we can define what's called a sequential execution. Okay, that means that the invocation is immediately followed by a corresponding response. Okay, there's no concurrency. Okay. The invocation on I is immediately followed by a response. That means there's no concurrency. Every invocation response, there's no overlap, to say it like that. They're all kind of non-overlapping. That means the whole execution is like one sequential sequence of things. Okay, so we can define that. Okay. And we can make some more precise definitions. a well-formed execution. The first event is an invocation, and a node alternates between invocation and response. Okay? And an operation is pending if it's invocate but not response, and it's complete if every operation is complete. So you have invocation and response. Okay? And you can also define the order now with events. An operation precedes another one if the response of this one is before the invocation of that one. Okay? And now we can define linearizability in a formal way. Okay? So we have some execution E. It's linearizable if there exists another execution such that E and F contain the same events. F is sequential, so there's no overlap. Okay? And the read response have the value of the preceding write invocation. So it's a legal execution. Okay? And if there's a precedence in E, we have the same precedence in F. That means you can map any execution to a purely sequential execution. And that's what it means to have a global single image. Okay? Of course, you have to worry about failures. You have partial execution, so some of the invocations have no response. And a partial execution is linearizable if you can add things to make it linearizable. You can add it by completing operations, either by removing the invocation or adding a response. But every operation has to be complete. And the final definition is sequential consistency. This is the same as linearizability. So we basically map an execution to a sequential execution F. F is sequential, F is legal, and instead of global time ordering, we have here local time ordering. Okay? This is only true per node. For linearizability, this was true globally, but now it's only true per node. So each node satisfies order, but not globally. And that's it. And then we're done for today.